the afternoon for some organic chemistry. A little bit of tea. I'll get around to that later. Organic chemistry revision. People ask for a revision. I asked people what they wanted. Some people said organic. So here we go. Organic stuff. I'm going to do organic mechanisms. I just want to say a little bit about organic chemistry first of all. To me, organic chemistry, there are three things you need to be able to do successfully. First one is the type of chemical you've got and therefore the name that it has. If you can do that, that's one of the three skill sets. So that's the first one, type, which includes naming. Then there's the sometimes quite overwhelming reactions and the reagents that you need to know to convert organic chemicals from one type to another, change the functional group. Around about 60 reactions you need to know what to do, how to do it, what you use in an A-level chemistry course. And then there's mechanisms. Mechanisms is a smaller set of reactions. You need to be able to apportion a mechanism to a limited set of reactions at A-level. And this video is going to focus on mechanisms. Before we can go wading into mechanisms, there's a couple of things we have to make sure. Firstly, do we know what a mechanism is? Mechanism is when you look at a reaction, it doesn't just go, oh, done. It's what stages does it go through, or what sort of sub-steps does it have. It's like when you make a cake. You don't go, here's the ingredients, oh, there's a cake. You go, here's the ingredients, first thing we have to do is this, then we have to do this, then we do this, and we put it in the oven or whatever. And then we ice it if it's Christmas. That's like a mechanism. So you break it down into stages that take place. And when you get further into chemistry, one of those stages will control how fast the reaction goes. That's called a rate determining step. That's a year 13 discussion concept. Now, when it comes to mechanisms, which is what this is about, there's a couple of things that we need to establish. First of all, the types of reagents, I suppose, the types of chemicals that you're going to use. Free radicals. One of the classic mechanistic questions is to do with free radicals, so we'll have a section on that. As you will see, I'll explain about how we're going to do with these videos. So free radicals. First thing, what are they? They have an unpaired electron. Most of the time electrons on chemicals are an even number, and therefore there's not an unpaired one. They're all paired up. When you get an unpaired electron, it's termed a radical or a free radical. In terms of your real world thing, free radicals inside your body are very bad for you. They are linked to cancer, I believe. How are they formed? Well, I'm sure there were lots of ways of forming them, but at A level, the only way you think about forming them is ultraviolet light acting on something that is diatomic. That diatomic is a halogen. So, and it's because the size of the UV photon is the same size as the bond energy of a interhalogen bond. So ultraviolet splits that up. So what you get bromine, for instance, would have a dot and cross diagonal like that. What you do is you send one electron that way, one electron that way, and the result, it's not negative, it's not positive, it has no charge, it's a bromine atom, and of course there were two of them because you started with the Br2. So free radicals. Then the other two electrophile. Electrophiles will have some way of being positive or partially positive. So what you're looking at is either something that is positively charged. Now most of the time that's a metal ion and they don't do organic chemistry, at least the majority of the time. So what you're looking at for almost all organic reactions, although there are some exceptions, is something that carries a partial positive charge. So when you look at something like that, that's the electrophilic end of that molecule because it's delta positive. There are times when you see, and this is a year 13 thing, you get that, which is also an electrophile, NO2 with carrying a plus charge. Well, that'll be an electrophile as well, but that's used in benzene chemistry, which is not a year 12 thing, which is what I'm doing at the moment. And then you have nucleophile. Now nucleophile, a bit easier to think about really, because it's the opposite. It's going to be a negative, either fully negative or partially negative. So you will get such things as things that are completely negative will be a nucleophile, Br minus, OH minus, all carrying a whole negative charge. Yeah. You will have things that are also not carrying a negative charge, but ammonia got an electronegative atom and lone pair. That makes that delta negative, and therefore that is going to be the nucleophile. Water will also fit that criteria because the oxygen is delta negative in water, two lone pairs as well. So therefore you will get water behaving as a nucleophile. So you can get nucleophiles that are either carrying a partial negative or a full negative. You can get electrophiles partially or fully charged. And that kind of finishes the introduction with the types of things. So there are just three types of reagent. There are the free radicals, really only occurs in one situation. Electrophiles, there are a whole load of reactions involving electrophiles, and then similarly a whole load of reaction with nucleophiles. And that's it really. So what's going to happen now is that there are going to be three versions of this. One of them is going to go on to do free radical mechanisms, one of them is going to be about electrophilic mechanisms, and the other one is about nucleophilic mechanisms. And it'll be whichever one follows what I'm saying now. I'll see you after the edit. Bye bye. So you're here because of free radical mechanisms. There are non-organic free radical mechanisms, but because this is about organic chemistry, we're going to focus on how this affects, well, alkanes and how they react with halogens. So, three letters up there, I, P and T, representing three steps. Initiation, propagation, and termination. Obviously the last one is the end thing. You'll see how that works. So initiation, there's only ever one initiation in the organic reaction set, and it's always triggered by ultraviolet. But what you do is you go from no free radicals to two free radicals. Propagation, now in any mechanism there are a whole collection of propagation steps, but they all have something in common. They all have a free radical and a non-free radical producing a different free radical and a different non-free radical. So what happens is it sustains the number of free radicals by converting one into a different one using a non-free radical. And a termination is two free radicals joining together. So what you end up with is a product has no free radicals. So you go 0 to 2, 1 to 1 or 2 to 0. And so initiation is the formation of two free radicals. Propagation is the sustaining of free radicals. And termination is the removal of free radicals. Now what happens then is that you get, I suppose you could say you get a whole load of products, but you get a major product and then you get a whole load of other products going on. You get non-organic products as well as organic products. Now if we take an example of, keep the thing fairly simple, taking ethane and reacting it with bromine. Now ethane would not react with bromine unless they were ultraviolet. So if you put ethane gas in a container with bromine, put it in a dark cupboard, you'll still have ethane gas and bromine, nothing will happen. However, if you expose it to, well, sunlight, got plenty of ultraviolet in the coming in from the sun, the bromine colour will fade. Flood it with ultraviolet light from a lamp, it does the same thing. So the overall reaction that is you see written down is that, barely enough board there, but that's not the only thing that happens. All that they've done here is said this is the most common set of products. So the most common set of products is you substitute, because you exchange a hydrogen for a bromine, substitution therefore, and that there is a very common product out of all of the set of possible products. HBr is the other common product where the other bromine out of the pair has picked up a hydrogen. However, other products are formed as well. One of the things that happens is you get this one then goes round and does the substitution and you get a dibromo compound, and then a small proportion of them go round and do 3 and 4, and you get a very small proportion where you've changed all 6 hydrogens for bromines. And then there's also the case where you get a different product, which would be butane, which we'll come to shortly. So, itchy nose. So, first thing is initiation. Well, I covered initiation in the little introduction, but the initiation, which I'm just going to write I for, is ultraviolet forming two bromines. Now you will sometimes see that written like that, that's a free radical. Sometimes you will see it with a dot. I like to do the dot because it reminds you that it's a free radical, but it is not essential that the dot is there for it to be a free radical nor marked correct in an exam. And that is, in this reaction, the only initiation that you will have. The energy of ultraviolet will not split off a hydrogen from any alkane. Ethane is R1. Now propagation, whole bunch of things. So C2H6, and then the only free radical we've got so far is a bromine free radical. It is a bromine atom, if you're thinking, is it a bromine atom? You're thinking right, it's a bromine atom. So what happens? Well, you've got a choice. It could lift one of the hydrogens from that, and then that, I'm not going to use the dot so you can see that it's a free radical, you will get that. But it's not the only choice. You could have had the bromine go in, leave you with a hydrogen atom or free radical hydrogen. So, two possible choices. This is a little more stable than this one, so you get a lot more of that one going on. So then, I said to you, it's not the only propagation step. So you then go, okay, so I've got a C2H5 as a free radical floating around in the mixture. What can you pair it up with? Well, you could pair it up with another bromine atom. Result, C2H5Br plus Br as a free radical. So what you're getting is one free radical, one non-free radical ordinary molecule fully complement with electrons in each one of these. So that's one possibility. So what has happened is the reason that this is written in the equation is we're forming this in more than one way, and therefore you get this as the most significant reaction. But you've got this free radical. So this could combine with, you could go, all right, there's a small amount of that, could combine with the bromine. There's a bromine free radical and an HBr. So we're yet again forming one of the identified products in the main reaction, and then you're getting a bromine free radical again. So you're getting the free radicals formed in a number of ways. The whole point of propagation is that there are multifarious versions of it, but in the end you get major things up here. But you could of course send this here, C2H5Br, round in its own propagation step and end up with it picking up another bromine and becoming dibromo in some form. Termination, any two free radicals join together to make a molecule. So you could just reform bromine, not very useful in terms of achieving the reaction, but it's going to happen because all possible combinations will occur. So if you took the free radical there and you took the free radical there, C2H5Br. So two free radicals forming a no free radical over here. Fits the termination step. Similarly, and this is where the reference to butane came in. I suppose I could have put a 2 in front of it, but two of those, very small number of them will actually meet up with each other, because most of the time the collisions will be with something else, and therefore you won't get two ethyl radicals, as they are called, joining together. But you put that together, C4H10, which is butane, or an isomer of butane if it's branched. So you can get a different alkane, but it will be at very low levels. So sometimes you do get the question, explain the formation of some kind of much longer or much bigger alkane from the starting material, and it's because you've turned that into a free radical, two of them are joined up and ended up with that. Now, with this lesson comes a sheet of things for you to try. The answers will be in a separate video, which I've yet to film, rather than as a written document, and the simple reason for that is that it'll take me so long to type it up because it's just really awkward, so I'm just going to do them on the board because it's easier. And therefore there is a sheet that goes with free radical mechanisms for you to try writing out free radical mechanisms, and I will write them out in another video. But at this point we have reached the end of free radical mechanisms. Should you want the electrophilic, in this case it will be electrophilic addition, and if you want the nucleophilic substitution, they are separate videos in the YouTube channel, and I look forward to seeing you there. Well, I say that, I can't see you, but if you're watching, thank you very much for coming. See you soon. Bye.